Black holes have long fascinated and haunted people with their mystery and strangeness. A large number of indirect signs have been observed confirming that black holes are widespread in the universe, but we cannot see them directly anyway. Astronomers speculate that it may come from the core of a large star that has collapsed and become very massive, dense, and gravitationally strong. There is also some observational evidence that supersized black holes exist even more at the center of many galaxies. Although humans have advanced astronomical observation equipment, such as large optical telescopes with sensitive photoreceptors, large radio astronomical telescopes to detect subtle electromagnetic signals, and the Hubble Space Telescope to roam in outer space, they are unable to see black holes. But recently, scientists have directly detected the intermediate mass black hole GW190521 for the first time, which is of great significance to human exploration of the universe. Black holes seem most likely to form where stars are most dense and where large masses of matter are likely to clump together. Because the central regions of globular clusters, the nuclei of galaxies, have this characteristic, astronomers are increasingly convinced that black holes exist at the center of such clusters. Some scientists have determined that there is a giant black hole right at the center of our galaxy, with a mass equivalent to 100 million stars, 1/1000 th of the total mass of the Milky Way, and 500 times the diameter of the Sun. If a star approaches it fast enough, it might be swallowed whole in one gulp. In fact, like white dwarfs and neutron stars, black holes are likely to have evolved from stars. When a star ages, its thermonuclear reactions have depleted the fuel in its center and there is little energy left to be produced from the center. Thus, it no longer has enough power to carry the enormous weight of the outer shell. So under the weight of the shell, the core begins to collapse until it finally forms smaller, denser stars that are capable of balancing with the pressure again. The less massive stars evolve mainly into white dwarfs, while the more massive stars have the potential to form neutron stars. And according to scientists' calculations, the total mass of a neutron star cannot be greater than 3 times the mass of the Sun. If this value is exceeded, there will be no more forces to fight against their own gravity, which would trigger another major collapse. This black hole, however, has a medium mass, which may not match the above description. As well as acting on accretion disks around black holes, magnetic fields may also have a significant effect on accretion disks around young stars and dense stars known as neutron stars. Cosmologists believe that there are many types of black holes in space, ranging from small black holes with a mass of a mountain to super black holes in the middle of galaxies. Scientists used to believe that once you fell into one, you couldn't get out, from giant stars to interstellar dust, and that even light was not immune. Professor Stephen Hawking's latest research on black holes threatens to disrupt this conclusion. After a long period of research, he has found that some of the matter swallowed by a black hole slowly flows out of it over time. This claim appears contradictory to the relevant theories of quantum mechanics, as modern quantum physics determines that this material information is never completely lost. Studying the nature of black holes helps us to understand the Big Bang singularity at the same time, because they are simply too similar to each other. General relativity predicts that moving, massive objects cause the radiation of gravitational waves, which travel through space at the speed of light. Just as the photons radiated by objects take away their energy, the gravitational waves radiated by objects will likewise take away their energy, so that systems of matter will eventually converge to a stable state. This is like throwing a piece of wood into a pond and causing ripples in the water. The ripples take the energy out of the piece of wood, causing it to eventually calm down. The gravitational waves generated by the Earth's orbit around the Sun cause the Earth to lose energy and its orbit gradually changes and eventually falls to the Sun, except that this energy loss is so small that it takes 100 billion years before they collide. When a star collapses into a black hole, the motion will be much faster and the loss of energy at this point will be much faster, so the collapse process will quickly reach a constant state. Because the state of a star before collapse is so varied, including its material form, mass, rotation rate, and the complex motions within the star, it seems difficult to make predictions about the final state of collapse. Canadian scientist Israel's research in 1967 was very surprising. He noted that according to general relativity, non-rotating black holes must be very simple, perfect spheres whose size depends only on their mass, and that any two non-rotating equal mass black holes must be identical. Initially, many scientists, including Israel, thought that since black holes could only be perfectly spherical, they should be formed by the collapse of an object with a perfect spherical shape. However, no star is perfectly spherical, so a black hole can only collapse to a point. And Roger Penrose et al. Propose an alternative explanation. The rapid motion of the collapsing star releases gravitational waves that bring the star closer and closer to a sphere, and when it finally reaches rest, it becomes an exact sphere. Thus, any non-rotating star, no matter how complex its constituents, mass and internal consequences, will end up in a perfectly spherical black hole after its gravitational collapse, whose size depends only on its mass. This idea was supported by further calculations and soon became accepted by all. At the same time, New Zealand scientist Roy Kerr calculated a family of solutions for describing spinning black holes in general relativity. These solutions show that black holes rotate at a constant speed and that their size and shape depend only on their mass and speed of rotation. With the faster the rotation, the more bulbous the equatorial part of the black hole. If the rotation is zero, the black hole is a perfect sphere. Israel's discovery is actually the special solution in the Kerr solution. The fact that black holes have no hair means that the complex and massive information about the characteristics of the object is lost in the process of forming the black hole. We will understand its significance in the next chapter. A black hole is a special case in the history of science, which has been developed to an extremely detailed level as a mathematical model, but for which there is still no 100% certain observational evidence. This redshift is so large that if it were seen as a gravitational redshift, it would be so massive and so close to us that it would interfere with the planetary motion of our solar system. So it could only be a redshift caused by cosmic expansion. A large redshift would mean that it is far away from us. If it can be observed at such a distance, it must be very bright, which means that it must radiate a lot of energy. Such a large amount of energy cannot be emitted by just one star, but is likely to be the gravitational collapse of the entire central region of a galaxy. Many such quasars have been discovered, but they are too far away to provide conclusive evidence for black holes because of the difficulty of observing them, and the discovery of neutron stars in 1967 gave encouragement for the existence of black holes. Since the radius of a neutron star is about 10 miles, it is only a few times the critical radius for the collapse of a black hole. It should be taken for granted that stars can collapse to much smaller scales. Because light cannot escape from a black hole, observing one is a bit like looking for a black cat in the dark of night. Thankfully, however, the gravitational effects of a black hole will still act on its neighboring stars. In the late 19th and early 20th centuries, there were two dark clouds in physics, blackbody radiation and the Michelson experiment. A year later, the first dark cloud gave birth to quantum theory, and 5 years later, the second dark cloud gave birth to relativity. After a century of development, two more dark clouds descended on the physics community at the turn of the century, the singularity difficulty and the difficulty of quantifying the gravitational field. These two difficulties may be resolved by the study of black holes and the Big Bang. The study of black holes and cosmology is closely related to elementary particles, the evolution of celestial bodies. In particular, the study of black holes involves some fundamental questions that help us to gain a deeper understanding of the natural world. Therefore, the present discovery of GW190521 is of great importance for human scientific research.